Okay, in the previous section on differential forms, we introduced differential one forms and differential one form fields and saw how those we could define a line integral in terms of those and work with those a little bit. In this section, we're going to focus on differential two forms and then k forms, where k can be, for us, 0, 1, 2, or 3. Since we're going to stick to R3, those are going to be the only ones. But first, let's recall a little bit what we did last section. So let's recall the differential one form, or sometimes we'll just write one form and just assume it's differential, so save a little notation, is given by its omega is a dx plus b dy plus c dz for some a, b, and c real numbers. So let's talk about a couple of things that we may have briefly mentioned before, but are going to be a little bit more important this section with differential two forms. So let's let v be a vector, say v1, v2 is our vector, and we're just going to take this in R2 just because it's going to be easier to draw pictures. Of course, you'll be able to easily generalize this to R3 as well. So we had, from last time, if we take dx, remember our differential there, dx inputs vectors and outputs scalars. Well, this just outputted to the x-coordinate, and dy just outputted to the y-coordinate of the vector. So if we think of that geometrically, what we have, let's draw our xy plane here. And let's go ahead and draw our vector in. So say this is our vector v. Well, we know if we drop this down, this distance here is v1, and this distance here is v2. So what these differentials are actually giving us is dx gives the magnitude of the x-coordinate of v. So let's put the v in there. And similarly, dy of v gives the magnitude of the y-coordinate of v. So that's what these things are doing geometrically. And of course, if we had three dimensions, we'd just have one more. We'd have the z dz, and that would give the z-coordinate as well. So one other thing we mentioned was we referred to these as oriented one forms. And this is going to be a little bit more apparent when we do things with two forms and so on. Because remember, we were very concerned with orientation when we were doing surface integrals. But we also had orientation that we were interested in when we were doing line integrals. We had to know which direction we were traveling on our path. So let's think of this. This is going to require a little bit of linear algebra, how I'm going to explain this. So if you haven't had linear algebra, you can go ahead and skip forward on this part. But so we were using and have been using the whole time the vectors I and j as a basis for R2. So what does that mean if you haven't had linear algebras? We always write our vectors in terms of this basis. So v is like v1i plus v2j. So we expand all of our vectors in terms of this basis. So now when we apply our dx and our dy, we're actually using this basis, right? So when we take dx of v, what is this doing? This is picking off the coefficient of I here. So this is giving me v1. So what we're doing is this orientation we're saying, when we say this is oriented, we're saying, well, we're picking a preferred basis we're going to use to define these differential forms. So for instance, we wouldn't have to choose I and j as our basis. So we could also use, well, infinite and many other bases, but a really obvious one, also use, say, minus I and minus j as our basis. And so what would that look like? Well, if I have v is v1i plus v2j, if I write it in terms of this new basis, this would be minus v1 times minus I plus minus v2 times minus j. So if I define my differential in terms of this basis instead, so let's use a different color to denote this in a little bit different notation. Let's say we defined our differential, and we'll call it, say, dx tilde. So this is defined in terms of the basis minus I minus j. So this has the different orientation. So different orientation. Right? So we can think of which basis we choose as our orientation. Well, now if I apply this to v, this is going to pick off my coefficient of minus I, so this would give me minus v1. So basically switching this orientation to a different basis gives us a different function here. So that's why we say, when we say that the dx and dy are oriented, it's because we're choosing a basis that we define them in terms of. So that's how you should think of this. We'll come back to thinking about this later in terms when we get back to surface integrals in a few sections from now. Okay, so let's go ahead and move along. So we want to move forward. So we saw how our one forms could be taken into account to do line integrals. So we've had a lot of other types of integrals we've looked at in Calc 3, though. So we want to move forward to be able to do area, surface area, flux, etc. integrals as well. So the first thing we're going to introduce is two forms. I guess maybe let's just introduce zero forms first, because those are the simplest. So if we remember, what did a one form do? So one form inputted a vector, inputted one vector, and outputted a scalar. So a zero form, then, this should input zero vectors and output a scalar. Well, if we're not inputting anything and we're outputting a scalar, a zero form is just a scalar then. For instance, 2 is a zero form. And then zero form fields, well, remember what that was is for each point we had, for one form, for each point we associated a one form. So in this case, for each point, we're going to associate a scalar. And so what is that? This is just a function. Right, so anytime we input a number and output another, each time we input a point and output a scalar, that's a function. So for example, we could say f of x, y, z being x squared y plus z. This is a zero form field. So that's pretty easy. This is just new language for something we've worked with for a long time, just functions and scalars. So now let's go ahead and do two forms. So these are a little bit more complicated. So what should we want from this? Well, we want to input two vectors and output a scalar. And now there's lots of ways we could do this, but we also want this to have something to do with geometry. We don't want just anything here. So let's see how we can define these, and then we're going to see what they're actually telling us geometrically. So let's take two vectors. So v is v1, v2, v3. And w is w1, w2, w3. So I'm going to define this symbol here, dx, and this is read dx wedge dy. So this is a new thing we're defining. This is going to be a 2 form. And so I want to tell you, what does this do when I input two vectors v and w to this? So how I'm going to define this is I'm going to define it as the determinant. And I'm going to take, in the first row, I'm going to, since I have the dx here, I'm going to take the x coordinates of each of the vectors, so v1 and w1. In the second term here is dy, so I'm going to take the y components of each one, so v2 and w2. And then, of course, the determinant of this is v1 w2 minus v2 w1. And no, sometimes we write this as v1 w1 v2 w2. So either notation is fine for that. So that's one of the 2 forms. Let's think of a different one. What if we did dy wedge dx and did v and w? Well, in this case, let's use the line notation here. Since dy is first, we take the y components first, and then we have the x components second. So this is v2 w1 minus v1 w2. And this really isn't anything too exciting, because if we notice, this is just the negative of what we just did. So notice this is dx wedge dy on v and w. So that's not particularly interesting. It's the same thing, only throwing, we need a negative sign in front of that. So we didn't really get anything new by changing the order from dx to dy, but we can define other ones as well. So if I did dy wedge dz, say, of v and w, this would be, I take the y terms first, so v2 and w2, and then the z terms second, so v3 and w3. And so this is v2 w3 minus v3 w2. So that's how we define these 2 forms. So you can, let's try one more example here. What if we did dx wedge dx of v and w? So this is v1 w1 v1 w1. This is v1 w1 minus v1 w1, which is 0. So you should convince yourself, say as an exercise, that, say, d alpha wedge d alpha is equal to 0 for, let's say, alpha can be x, y, or z. We just did the x version, but you can see it for y and z. And then all combinations of d alpha wedge, say, d beta for alpha equal to x, y, or z, and beta equal to x, y, and z can be written as plus or minus of just 3 of them. So we can have dx wedge dy, dy wedge dz, or dz wedge dx. And we're going to see why we choose those particular ones in a little bit. But just like above, we saw that dy wedge dx was just negative of dx wedge dy. Go ahead and show that for all of the other ones as well. So it's really these 3 are the only ones we care about. Okay, so let's see what these things are telling us geometrically now. So let's just start in 2 space first. So what is the geometry here? All right, because we said that this should be telling us something about area, so let's think about that. So let's start in R2 first. So do the easier to draw case first. So let's think of what our vectors v and w look like. So I've got this vector, say, v here, and this vector, say, w here. Now, if I were to take this and extend this out, remember we looked at this before, back when we were doing cross products, and we look at this parallelogram here. Hopefully we remember the area of this. So this has area given by the magnitude of v cross w. Well, let's go ahead and calculate what that magnitude is. So if I have V cross W, in this case, since I'm just taking in just the xy plane, I have V1, W1, V2, W2. And if you calculate this out, this is V1, W2 minus V2, W1, K. So then the magnitude of this is just the absolute value of V1, W2 minus V2, W1. And hopefully this looks familiar because this is exactly what we just had up here when we did this calculation, V1, W2 minus V2, W1. So this is the absolute value of dx wedge dy of VW. So what does this tell us? Well, this tells us that this quantity dx wedge dw of VW, well, it's giving us the area of the parallelogram spanned by V and W, but it's giving us a signed area because we don't take the absolute value. And that's exactly the same thing as taking choosing which vectors come first. So this is the signed area of the parallelogram spanned by V and W. So notice here, if we changed the order, this would be W1, V1, W2, V2, which would be W1, V2 minus V1, W2, which is the negative of what we had before. So that's what we mean by it's choosing the signed area, is that when we choose, the way we define dx dy is we input v first and W second. So when we're looking at this parallelogram up here, when we take dx wedge dy and then we do v and w, that gives us one version of the area. And if we were to do, okay, well, let's do w and then W first and then V, we would get a negative sign of the area. So that's what we mean by the orientation here, is we know this area is just a number, but based on the choice of which we take first tells us whether we're going to get one sign or another. So we have the oriented area there. So also the signed area. So what about if we were to do things in 3 dimensions? So if we did things in 3 dimensions, it's a little bit messier to draw. But so what about 3 dimensions? What's the geometry there? Well, in this case, let's go ahead and draw this out and do the best we can with the picture. So if I have 2 vectors now, so let's say I have V going like this, maybe W going like this. Well, I can think about what happens when I drop them down into the plane. So this would be a vector down here, and then I get another vector down here by dropping this one down. And then I get that parallelogram again spanned by these 2 down in the plane. So what would these vectors be? This one, when we drop this down, this is V1, V2, 0, and this one is W1, W2, 0. So if I do dx wedge dy of VW, well, we saw already that this is the V1, W1, V2, W2, which is V1, W2 minus V2, W1. And that's exactly the signed area of this, of the projection. Okay, so this whole thing up here would form, this would form a parallelogram in 3 space. And what we're doing is we're projecting that down into the xy plane. So this is projection to the xy plane of the parallelogram in R3 spanned by V and W. So it's still just giving us this area. So that's the geometry of these kind of basis vectors for the two form. So that's quite nice. We're actually getting some interesting geometry here. So let's go ahead and define our two forms. So a two form, general two form, is written as, so we have omega, we'll call it that again. And now we're just going to choose those three interesting ones before. And we're choosing a little bit different order than you might have thought. But we'll see why later we choose this. But you can kind of think of this, if you were thinking of the y and z as kind of your I and j, just kind of telling us our directions here. So if this is x, y, and z, if I did y here and z here, and I did y cross z, that would be going in this direction. So it'll be going, so if I have j, k here, then j cross k is equal to I. So that's kind of what you want to think about this is kind of the x direction here. And so on for the other two. So that's kind of the reason we're thinking of this in this direction. So just kind of look at the other two and think of the right-hand rule, and you'll kind of see that the second term there is looking like what your j would, and your last term is looking like what your k would. Okay, so let's try a couple of examples here. Get used to working with these two forms. So let's first consider, let's make w to be 2 dx wedge dy plus 3 dy wedge dx plus 6 dy wedge dz. And let's write this in our form. All right, so we want to just use those three vectors above. So just note that if I take the 2 dx wedge dy, so dx wedge dy was one of the ones we used. Now dy wedge dx was not, but we know we can change the order of that by using a negative sign, plus 6 dy wedge dz. And so this becomes negative dx wedge dy plus 6 dy wedge dz. And then if we want to write it in the form above, we'll just change the order. So we're going to need to use this because when we'll be taking some wedge products eventually, and between different forms, and we'll need to be able to change the order like this. Let's try one more example just to remember how these things work. So let's let omega be 2, say dy wedge dz plus 3 dz wedge dx plus 4 dx wedge dy. And let's calculate omega of VW for V being, let's just take the vector 1, 0, 2, and W be the vector minus 1, 1, 3. So then omega of VW is 2, and then when I plug in V and W, I have Y and Z, so this is going to be 0 and 1, and then the Z gives me the 2 component and the 3 component. I have plus 3, and now I take the Z component first, so I'm going to get 2 and 3, and then the X component, so I'm going to get 1, negative 1, and then finally 4, and I take the X component of each first, 1, minus 1, and then take the Y component, 0, 1. And then we can just evaluate these determinants. So this is 0 times 3 minus 2 times 1, plus 3 and 2 times minus 1 minus 3 times 1 plus 4, 1 times 1 minus 0, 1, negative 1 times 0. So this gives me a minus 4 for the first term. And then here, this gives me a negative 2, negative 3, so negative 5, so negative 15. And then this last one gives me plus 4, so this just gives me the value negative 15. Okay, so that's how we work with two forms. But remember when we did one forms, what we really were interested in eventually to do calculus was one form fields. So we want two form fields here as well. So what do these look like? These look like functions outside our, instead of constants out front, they're functions. Just the same way we did in the one form case. And a lot of times to save notation, I won't write the x, y, and z in. We'll just write it like this, with the understanding that these are functions out front. Okay, so remember for this, what happens is we input a function, or we input a point to get a two form, and then we can evaluate that on vectors. So let's just do a quick example here. So let's let omega, we'll say this is y dy dz plus x squared dz dx plus yz dx wedge dy. And we'll let our point P be the point 1, minus 1, 2. So then the two form, WP, remember we evaluate the functions out front of this. This is negative 1 dy wedge dz, because we plugged in the negative 1 for y, plus 1 squared dz wedge dx, plus negative 1 times 2 dx wedge dy. So this is just negative dy wedge dz plus dz wedge dx. So minus 2 dx wedge dy. So at that point P, this is our two form. And now we can evaluate this on vectors. So if we let B be, say, 1, 0, 2, W be negative 2, 1, 3, then WP of VW is just negative, and then again we do, so we have 0, 1, 2, 3, plus, and then we do the z terms first, so 2, 3, and the x terms 1, negative 2, minus 2, and then the x terms 1, negative 2, 0, 1. And working all this out just gives me a negative 7. So that's how we do two forms in two form fields. So let's move on to three forms now. We've done 0 forms, we've done 1 forms, we've done 2 forms. It's time to do 3 forms. So for a 3 form, we should have an input of 3 vectors and output of scalars. So we want to input 3 vectors and output a scalar. And we saw 1 forms give us something along with line integrals, and 2 forms there we saw that those were measuring areas and projected areas. So this should somehow give us something to do with volume. So we're going to define our 3 form. There's only going to be one of them, and it's going to be dx wedge dy wedge dz. This is our 3 form. And if we input vectors u, v, and w, this is just going to be the determinant of u1, v1, w1, so the x coordinates, because the dx is first, and then we're going to do u2, v2, w2, because y, and then u3, v3, w3 for the third term. And so, of course, we can also write this with just the lines with that notation if we want. And then to just refresh our memory on how we do this determinant, I'm going to go ahead and say I'm going to expand in the first term, so this is going to be u1 and the determinant of v2, w2, v3, w3, and then minus, and I'm going to go down the first column here instead of along the first row. So this is going to give me a v1, w1, v3, w3. And the reason for doing this, we'll see in a second, is this is an easier way to see the volume, that this is giving us some volume. So we're going to do plus u3, and this one's going to be v1, w1, v2, w2. So this is u1, and then I have v2, w3 minus v3, w2 minus u2, and then this is v1, w3 minus v3, w1 plus u3, v1, w2 minus v2, w1. Now, this is a nice formula here. It doesn't really look like anything too familiar, but let's think about something here. So if we take v cross w, and we work this out, this is exactly v2 w3 minus v3 w2I plus or minus v1 w3 minus v3 w1j plus v1 w2 minus v2 w1k. So what that shows me then is if we compare these two formulas, what we have is dx wedge dy wedge dz of u v w is the vector u dotted with the vector v cross w. And now how is this telling us anything about volume? Well, let's draw a picture here. So let's take our vectors, and so let's say I've got v here, and let's take w going in this direction, and then let's take u going like this. Now, if I form a parallelogram on the bottom here, we know this thing has area magnitude of v cross w. And so what I'm going to do is I'm going to take, if I take the cross product of those, so this is v cross w, that's a vector going in that direction. And now I can take the projection of u onto that, and that'll be a vector, say, going like this. So this is projection of u onto v cross w. And so that, if I construct a three-dimensional region now, like this is called a parallelepiped. So the height of this thing, so this has base area magnitude of v cross w, and height, well, that's going to be the magnitude of the projection of u onto v cross w. So that means this parallelepiped has volume given by the height, which is the magnitude of the projection of u onto v cross w, times the area of the base, which is v cross w. Okay, so that's just a geometry thing. We could have done that a long time ago. How does this help us with what we're doing so far? Well, let's actually calculate a formula for this. So the magnitude of the projection onto v cross w of u, well, this is the magnitude of u dot v cross w. So this is just our formula for the projection vector. Magnitude of v cross w squared v cross w. So if I take the magnitude of that, this just gives me, the top part is a scalar, so I just get this, and then one of the v cross w's cancel, so I have a v cross w in the denominator. So then my volume is equal to, remember, it's the magnitude of this projection, so absolute value of u dot v cross w over v cross w, and then the area of the base, which was v cross w. So this is just the magnitude of u dot v cross w. So that's pretty cool because that's exactly what we had before. So this is, remember that our dx wedge dy wedge dz of u v w was u dot v cross w. So again, we're getting assigned volume here. So since the volume is the absolute value, we get a signed version of this. So dx wedge dy wedge dz, this is usually referred to as the volume form. And now notice here, we could change the order, but if I change the order, so if I were to look at like dz wedge dy in this order, well, we can always flip these. So this would be dx wedge, and then I get negative dy wedge dz from flipping the order, and I can pull that negative out front. So I just get the same thing with a sign back. So you can go ahead and check as an exercise that any ordering is equal to dx wedge dy wedge dz up to plus or minus sign. And so our three forms are just going to be a dx wedge dy wedge dz for a real number, and our three form fields are just going to look like f of x, y, z dx wedge dy wedge dz. So those are our three forms. So the last thing we want to introduce for this section is, what about higher forms? So what about k forms for k bigger than or equal to 4? Well, for R3, there aren't going to be any. So for instance, how would we try to define this? Well, we could try to say, if I had 4 vectors, say, well, the way we've been defining this is in terms of a determinant. So this would be the determinant of u1, v1, w1, x1, u2, v2, w2, x2, u3, v3, w3, x3, and u4. Oh, wait, these are just 3, sorry. That's all of them, because there are 3 coordinates. We know this has to be 0 because the dimension of R3 is 3, so any collection of 4 vectors must be linearly dependent. So there isn't anything that, so this determinant wouldn't work. Another way to think about this is, if I had dx wedge dy wedge dz, I'd want to include one more term here to get a 4 form, but I can't really do that because, for instance, if I tried to wedge this with dx, if I move this dx through, so this would be negative dx wedge dy wedge dx wedge dz, and then another negative would make it back to positive. But then the dx wedge dx is 0. So we wouldn't have anything there. So nothing will work for this. And of course, if you go bigger than 4, it's even worse. So there's no 5 forms, there's no 15 forms on R3. Now, if you go to higher dimensions than R3, then there will be. But we're going to stick with just 3 dimensions for this. So what's next? So in the next lecture, we're going to introduce the exterior derivative. So what good is this? Well, this is going to take us, so the exterior derivative will move from like a k form to a k plus 1 form. So they'll take like 0 forms to 1 forms, 1 forms to 2 forms, and etc. And what this is really going to do is this will kind of bring together the idea that I've said before, that the gradient of f the curl of a vector field and the divergence of a vector field are all, I always said they're like a derivative. Well, this exterior derivative will show us exactly what that means by saying these are like a derivative. So that'll be in the next section.